Now, an algorithm is, well, to understand what an algorithm is, I think we first need to understand why computers exist. Now, the reason computers exist is, I think specifically, the first thing computers were made for. It was to automate a task previously done by humans, and this was printing out log tables, which was a very laborious process. So, by making this machine, now called computer, it was automatic and easy and not error prone, no human error in making log tables. Now, computers are not humans. They do not understand. You cannot tell a computer, you know, make me coffee, and then they can just instinctually pick up, well, not instinctually, but subconsciously pick up a cup, do all the necessary, like even when you're walking, synchronize your left and right foot while you're walking, and your hands with your feet. You're swinging them in a synchronous way. When you're picking up a cup, you have to extend your arm. You have to have a specific degree that your arm makes when you're extending it. There's a lot of details, a lot of complicated processes that you do just to pick up a cup. Then you have to know how much coffee you should put, and then relative to that, how much hot water you should put. Like there's a lot of parameters that you need to nail down to make coffee. Now, for the computer to do that, you have to tell it exactly, step by step, how to make a coffee. You cannot just tell him make a coffee, and you cannot tell him to just do it like we can to another human. So this is actually called an algorithm. An algorithm is simply a set of instructions that achieve a goal in a well-defined, non-ambiguous way. So if you give this set of instructions to anyone, they will understand them as anybody else, and they will have the same inputs, the same things they can work with to achieve the same goal, the same output. Now, in the real life, one example was making a coffee, but there are a lot of complex scenarios we do on a daily basis that we can call algorithms. Well, since I love coffee, I'm gonna go with another coffee example. If you go to a coffee shop to order a coffee, that in itself could be defined as an algorithm. I mean, the act of buying a coffee, you could define it with an algorithm. For example, when you're walking into the coffee shop, you first have to open the door, then you have to close the door, then you have to walk over to the barista, then they ask you what you want to drink, then you have to decide what you want to drink, then you need to tell them what you've decided on, then they're gonna ask you what's the size cup of, like the size of the cup you want. Then you have to tell them among 3 options or 4 options or whatever which cup size you want. Then they will ask you the preferred way of payment, cash or card. Then you have to choose one of those and then tell them that. And then finally you can pick up your coffee. And this can be written as a series of steps. And when you do that, even though it's not something you would usually do because it's on a very high abstract level, but you could write this as a series of steps and call it an algorithm, because that's all an algorithm is. I want you to understand that an algorithm isn't anything special. It's just a set of instructions that lets anyone understand how to achieve a goal. And this is understood the same way by everyone. So there's no ambiguity, and it's well defined. Now, let's move out of the sphere of real-world examples. Because real-world examples are too abstract, and usually we use different sort of visualization, or not even visualization, but illustrations and diagrams and different things because of the abstractions rather than algorithms. Algorithms are used to express something in all of the it captures all of the possible details, so it tells someone how to exactly do something. But if we talk about the coffee shop and everything, we don't really know what does it mean to open the door. I mean, we don't talk about the degree of the arm, we don't talk about how much we should extend it, we don't talk about any details. So usually algorithms aren't used in abstract cases. So for example, a real example where an algorithm would be used is the max element function. So if you want to find a maximum element in a list and you want to code that for a machine to do, so you give the machine a list, it tells you the largest number. To do that, generally what we want to do is we want to verbally express how to do that so that we can have a good understanding. Then we would try to write that in pseudocode. I'm going to talk about pseudocode in a little bit. And then finally we'll translate that to a real programming language and actually make the machine do it. Now, for example, if I asked you in this list to find the largest element, you would obviously see that it's 27, but how did you do that? What was the exact process your brain took to find that to find that 27, to conclude that 27 is the largest number? You will probably have a hard time answering that question because it's very obvious. You just see 27 is the largest and you say, okay, 27 is the largest. Now, a computer cannot just do something. Nothing is obvious to a computer. It's a piece of hardware. It doesn't have a brain. So you have to define this in a well-defined, step-by-step instructions way to explain to the computer how to find that largest number. So that's the first problem. The second problem is, if I give you this list, which is a pretty large list, and if I asked you what's the largest number here, it wouldn't be so easy anymore. So, in fact, with the absence of knowledge of how you found the largest number in the short list, means that you cannot find the largest number in the long list. So we have to express this, at least verbally for now, how we found the largest number in the short list. And we also, whenever we're trying to, so we have the first, second, third step of first step, verbally expressing the algorithm, second step, expressing it in a pseudocode, and third step, implementing it in a programming language. When we're doing the first step, and when we're thinking about an algorithm, you really want to work with the minimal samples that reproduce that example. So, or at least near minimal. So that's a short list, for example. The minimal would be a single number in a list or two numbers, depending on how you look at it. But if we work with a short list, it's going to be easier. Now, I could say here, I can propose an algorithm right now. I can keep track of the greatest element found so far when I'm going through the list from left to right. And the process of how I'm ensuring it's the greatest one will be as following. So first of all, I will assume the first element of the list is the greatest element encountered so far, because that's true, because we haven't seen the rest of the list. Imagine you don't see the rest of the list. Imagine you just see the first element. Imagine you see just one element at a time through the list. So we say that the first element is the greatest element we've encountered so far. Now, I don't want to say greatest element encountered so far a million times, so I'll just call that a G. It's like a symbol, G. When I say G, it means greatest element encountered so far. So, G is now the first element. So, we go to the second element. We will call the current element we see, because we said we only see the previous elements and the current element. We don't see the rest of the list until we actually go there. So the current element we see we'll call X. This is the symbol for the current element. So we say if X, we check if X is greater than G. So if the current element is greater than the greatest element encountered so far, then G should equal X, meaning the greatest element found so far should be the current element because it was greater than the previously greatest found element. And if we continue this process up until the last element, up until when X becomes the last element and we do this check, we will have ensured that G is the greatest element in the list. Now, when verbally expressed, even though you may, to beginners who don't know what pseudocode is, even though it may sound better to verbally explain an algorithm, it really isn't, because first of all, everyone talks differently. The use of language is different for everybody. It's subjective. It's not well defined, and it's ambiguous. And it's very lengthy. It just took me a long time to explain a very simple algorithm verbally. But if we boil this down to pseudocode, and this is the pseudocode for this algorithm. I will not explain right now the pseudocode. We'll see what it is, because you have to know some concepts of programming, because pseudocode is very closely related to actual code. But you can see how short the pseudocode is. For now, all you need to know is that pseudocode is basically like code that you will write in a programming language, but it does not adhere to any rules of any programming language, because adhering to syntax rules of programming languages and other rules, it's necessary, of course. It's there for a reason. But when we're trying to conceptually think and come up with an algorithm, it can be limiting and time consuming and deteriorating from our goal of finding an algorithm. So we use pseudocode in which it is obvious what we want to do, but we don't want to adhere to any specific limitations of how we can write things. So you can write, for example, in pseudocode to say symbol equals something. By symbol, I mean variable, and we'll see later what that means. You can use equals, or you can use like an arrow pointing from the value to the variable. But the important thing is pseudocode is just a relaxed way of writing code to communicate your idea, your algorithm. So next we will see a more complex algorithm, sorting a list from either largest to smallest or smallest to largest element. And yeah, that will be our next topic.